last video we introduced Newton's second law, and Newton's second law was F equals ma. And what we learned from it really is that a, the acceleration of an object, is equal to its force divided by its mass. And looking at this equation, and you should always try and look at equations and say what do they mean. This tells us that if the force number gets bigger, if this number gets bigger, if force increases, the acceleration will increase. But if the mass number gets bigger, if the mass of an object gets bigger, the acceleration will decrease. You know from fractions that the bigger the number in the denominator, the smaller the overall number. For example, you have 1 over 4, 1 over 8, 1 over 12. The bigger this bottom number gets, the bigger the denominator gets, the smaller the overall number. 1/12 is smaller than 1/8, which is smaller than 1/4. So we can see that from this relationship here. But that's not the full story really, because let's say we have, it's not just as simple as the force that's acting on an object. So let's say we have object A and there's 10 newtons being applied to it. And then we have an identical object B which has 20 newtons being applied to it. Well, from the last video, hopefully you'll say that, well, B will accelerate a lot more than A because there's a bigger force in it, and that makes sense. The bigger the force, the more it'll accelerate. But what if now I added another force on B in the backwards direction, which is 10 newtons? What would be the difference in their acceleration now? Well, to do this, we calculate what's known as the resultant force. A resultant force is the result of, what is the result of the two forces added together? So if you look at this and you imagine that, well, 20 people of exactly the same strength were pulling to the right, and 10 people of exactly the same strength were pulling to the left, you'd expect that these 10 people pulling to the left would cancel out 10 from this side. And the overall force, the overall effect really, would be 10 newtons to the right. So the resultant force in this case would be 10 newtons to the right. So this kind of shows us that A and B are actually identical. Even though they've different forces on them, the effect will be exactly the same. The resultant force is exactly the same, and you could have an infinite amount of these. You could have another block C which has 55 newtons going this way and 45 newtons going this way, and it would accelerate by exactly the same amount as A and B, because the resultant force would be 55 minus 45, which would be 10 newtons to the right. The only case, I suppose, where you need to be careful is looking at that direction of force. In that, let's say we had another force D, which had a force 30 newtons to the left, 20 newtons to the right. Now the overall resultant force on this would be 10 newtons. But it wouldn't be 10 newtons to the right, it would be 10 newtons to the left. So obviously that object is going to accelerate to the left instead. So when we use our F equals ma equation, the point of this really is when we use our F equals ma equation, it's not just the forward force that we should be using, it's the resultant force. So I often write a little F or here instead. So it's F or equals ma. So that's just a little add-on, and now we're going to look at a question or two. The questions come from the Folan's textbook, Fundamental Applied Maths, the Oliver Murphy book, and this question is on page 68 of that book. So I'm going to go through hopefully one question, maybe two questions this video. I might have to do another one because I have to keep the videos a certain length on YouTube. So let's look. We have a car, and that car has a mass of 1,500 kg. And by the way, if I'm ever going too fast, all you need to do is pause it and take a breather and take some notes, or replay things if you need to. Its engine produces a tractive force. Now that tractive force is just the word we use for pulling force. So that's the forward force. Let's say this is the car and this is the front seat, of magnitude 5,000 newtons. Now one thing I always suggest you do for this is draw a diagram. Always draw a force diagram. There is air resistance of magnitude 2,000 newtons. Ignoring friction, find the acceleration of the car. Well, our equation is F equals ma, So if we want to find acceleration, that will rearrange to be F over m. Be careful, it's not 5,000 newtons over 1,500, because this is the forward force, but really we should be looking at the resultant force. So we don't use that. What we do is we calculate the resultant force first, which is going to be 5,000, take away 2,000, which is 3,000 newtons. Type that into your calculator and you'll get an answer of 2 meters per second squared. And that's the answer to the first question. So that's nice and easy, but that's just an introduction into making sure you use the resultant force. Let's look at another example and let's see how these combine with the questions we've done from topic 1. So we have an Inuit pulls a sleigh from rest. So the sleigh isn't moving at the start. The sled and the luggage have a total mass of 800 kg. The Inuit pulls it by means of a light, horizontal, inextensible rope. There's no friction and the tension in the rope is 100. So we have our sleigh and the Inuit is pulling it with a force of 100 newtons. The sleigh and luggage has a mass of 800 kg. 1. Find the acceleration. So that's easy. A equals F over m. We've no backwards force this time, so our F4 is just going to be 100 divided by 800. Let's leave that as 1 over 8 meters per second squared. And don't forget the unit for acceleration is meters per second squared. Part 2. Find the distance covered in the first 10 seconds of motion. Now what you're going to see in other topics is topic 1 actually comes into them a lot as well. So anytime we have anything which is accelerating at a constant rate and we want to find something like the distance or the time traveled or whatever, we always use our UVAST. So we're going to be using information we learned in topic 1 here as well. So the sleigh started at rest, acceleration is 1 over 8, and we're looking for the distance traveled in 10 seconds of motion. Now you should be fine with this, so I'll go through this fairly quickly. We're just looking for the distance, so it's S equals UT plus a half AT squared. So it's 0 times 10 plus a half, 1 over 8 times 10 squared, and you get an answer 6.25 meters. And that's your answer, because 0 times 10 goes to 0, so we're just looking at the second bit here. Okay, I'm going to actually try one last question here, again from Folens on page 69. We have a bullet of mass 80 grams is traveling, what's on here, my pen seems to have broke. Oh. A bullet of mass 80 grams is traveling with a velocity of 800 meters per second when it hits a tree. It stops when it becomes embedded in a tree 50 centimeters from where it enters. So let's just have a look at this. We have a tree and we have a bullet. And the bullet is traveling at a velocity of 100 meters per second, hits the tree, and obviously it travels a bit into the tree before it stops. The distance it travels into the tree is 50 centimeters. Now remember, we never leave centimeters as centimeters. We have to change that to meters, so that's 0.5 meters. It has a mass of 80 grams. This is the next thing now as well. We never leave mass in grams. We always must convert it to kg. So how you convert grams to kilograms, I'm sorry, that's really messy, is you divide by 1000. So anytime you see a question, and that's important to make a note of, your mass must be in kilograms. So this will become, sorry about the dog there, 0.080123, kg. That's the mass. So obviously here, its final velocity is 0 meters per second because it stopped. So what we have here is we have deceleration rather than acceleration. And remember, deceleration is just a negative acceleration. So find the resistance of the wood of the tree, assuming that it's uniform. What they mean by that is, well, what's the resistive force? So what force is slowing it down? So if we want to find this force, the force that's slowing it down, we need to know its mass and we need to know its rate of deceleration, which is just negative acceleration. We know the mass, 0.080 kg, we just need to find A. So how will we find A? Well, anytime we have acceleration and distance and time and all these things, we're using UVAST. So we use UVAST to find what our deceleration is. Initial velocity was 100, final velocity was 0, and the distance it travelled was 0.5 meters. Finding A, we'll use v squared equals u squared plus 2as. So rearrange that. A equals v squared minus u squared over 2a equals 0 squared minus 100 squared, and you can check all of these over 2 times 0.5, and you get an answer of minus 10,000 meters per second squared. And you see how you get the minus because it's a deceleration, it's slowing down. And finally, and I'm going to do it quickly because I'm going to run out of time, if we want to find the resistance to the tree, F equals ma, it's going to be its mass, which is 0.08 times minus 10,000 equals minus, where are we going? Minus 800 newtons. And that's your answer to part 1. Okay, part 2, because I'm out of time, I'm going to ask you to try yourself. The solutions are on page 69 in the Folan's book, but I can easily make another video if you need me to. But have a look at the stuff, these couple of examples that we went through in the Folan's book as well. And remember, if I'm going too fast, you can pause it, slow it down, rewind it, and watch it again.